In this lecture, we're going to discuss the Euler characteristic and show that it is well defined. Now, those of you who have taken topology A, it's not required, but if you took topology A, we talked about this thing called the Euler characteristic of a surface. And we used the fact, but we never proved it, that the Euler characteristic of a surface is well defined. In other words, it does not depend on how you triangulate your surface. Also, we can talk about the Euler characteristic of a graph. So if G is a topological graph, so if G is a topological graph that has been triangulated to have V vertices and E edges, then the Euler characteristic of the graph is equal to the number of vertices minus the number of edges. This came up when we talked about the fundamental group of a graph, and we saw that it is determined using this quantity. So this is the way we saw that the Euler characteristic is a topological invariant, because it helps us compute the fundamental group, which is a topological invariant. Now, if you have a surface, then it's similar. So if S is a surface. Now, if you're not sure what a surface is, do not really worry about it, because we'll give the most general definition rigorously. But if S is a surface with that has been triangulated with V vertices, E edges, and F faces, then the Euler characteristic of the surface is then equal to V minus E plus F. And the pattern here is very simple. Vertices are of dimension 0, and edges are of dimension 1. And here the pattern would be this is of dimension 0, edges are of dimension 1, and faces, which refers to triangles, are of dimension 2. So you get to see the pattern. The pattern is it alternates. You start with dimension 0, and then you alternate plus, minus, and so on. And that's how you can define the Euler characteristic of a more general topological space. But it has to be a topological space that has a triangulation. So if you assume that the space could be triangulated, then this is the way you will define the Euler characteristic of that space. And we will show that this quantity is well defined. In other words, it does not depend on how you triangulate. So even though these numbers, V, E, F, and so on, even though those numbers depend on how you triangulate, the Euler characteristic is a topological invariant, and it never changes. And the history of this, of course, for those of you who might not know, I imagine most of you probably know this, but the history of this, it came up in geometry, that Euler realized that if you have a polyhedron, so let's say a convex polyhedron, so let's say you have like this prism over here, that's a prism, or maybe you have a pyramid, or maybe you have a tetrahedron, maybe you have a cube, so on. That he realized that no matter what kind of polyhedron you have, now you want to be a little bit careful. It has to be a polyhedron that does not have a hole in the middle. So the easiest way to do this is by saying it's a convex polyhedron. So if you have a polyhedron, convex polyhedron, and then you count how many vertices you see. So here you see on the prism, you have 6 vertices. Then you can count the number of edges. You have 1, 2, 3, 1, 2, 3, and then 1, 2, 3. So you have 9 edges. And then you count how many faces. You have 1, 2, 3 on the side, and then 5. Okay. So then if you were to do this calculation, vertices minus edges plus faces, here you end up getting the number 2, 11 minus 2. So you end up getting 2. And if you do it for a pyramid, you would get 2. If you do it for a tetrahedron, you would get 2. If you do it for a cube, you would get 2. You will always get the number 2. And the reason for this is because topologically, all of these are homeomorphic to the sphere. So that's why we say that Euler inadvertently discovered one of the first instances of topology. Even though he was not thinking about topology, and he was not thinking of these as being homeomorphic to the sphere, he was just thinking about geometry, and more specifically, he was thinking about polyhedron. So even though that is what he was thinking about, he still discovered a topological invariant that they all have. For those of you who might be a little bit worried about faces, because we are talking about a triangulation, so if you're bothered by the fact that, let's say, on a cube, how are we allowed to count this as a face? Well, all you do is you just can further triangulate if that bothers you, like this or something, and you make them triangles. The fact that you would count, let's say, the square base of a pyramid as a face, or the one that's facing you as a face, you count that as a face, even though it's not technically a triangle, is not a big deal, because you can just cut it down through a diagonal and then make it a triangle, and it's not going to change anything. So that's what we call the Euler characteristic. And now we proved that the Euler characteristic for a graph is a topological invariant by using the fundamental group. So the way that went was, let me just quickly remind you how that goes. So what we proved is that the fundamental group of a topological graph, it's a free group of rank 1 minus the Euler characteristic of the graph. And this shows that the Euler characteristic must be a topological invariant, because the fundamental group is a topological invariant. And we're going to do something very similar to the Euler characteristic of a topological space in general. But first, we should define the Euler characteristic in general. So here's a definition. Let X be a space, a topological space. So we say that a collection, let's call them F lambda. We're going to assume that lambda is a finite set. We say that a collection of maps, a collection of maps F lambda from, we say a collection of maps, well, let me start again. So a triangulation of X is a collection of maps so that F lambda is a map from a geometric simplex. I write it this way to indicate that the dimension of the simplex depends on the index. Because when you triangulate, you have vertices, edges, faces, and higher dimensional simplices as well. So you cannot assume that they all have the same dimension. So more generally, these are just geometric simplices of different dimensions. So you have these maps into X, so that you have these maps, and each F lambda maps this geometric simplex homeomorphically onto a subset of X. By the way, this subset, it must be closed. Not that it really matters first. If you assume that X is Hausdorff, which is typically what we do anyway, the image, this is compact, so the image is a closed subset. It's a compact subset of a Hausdorff space, so it has to be closed. But that's some irrelevant point set topology. It's completely irrelevant for us. So each F lambda maps these homeomorphically onto a subset. It happens to be closed, but that's not a big deal. So that the union of all of those subsets, they give you X. And if you have X lambda 1 intersect X lambda 2, then they intersect at a common face. It could be the empty face, by the way. If the intersection is empty, we call that an empty face. I do not want to say any more on this. I want to intentionally leave this a bit ambiguous for the simple reason because we defined it rigorously a while ago. So if you want to go back to that lecture, you can look up the careful explanation of what that means. The issue, of course, is what exactly do we mean by a face? And that's something I do not want to define again because that's going to take us on the detour, and we're not going to even need it in the lecture. So that's why it's sort of like a waste of time to go over it again. But if you're interested to see exactly what this means, you can just go back to the lecture that when we talked about simplicial homology, and then you'll see well, it was the lecture on computing homology, and then you will see what exactly that means. Okay, and then you let, okay, so that's what we call a triangulation. And then you're going to let script K be the corresponding simplicial complex with respect to this triangulation F lambda. So how do you get the corresponding complex? Well, just to quickly remind you how it works, if this blob represents your space, and you have an F lambda, and F lambda maps, let's say, a two-dimensional simplex into X, then if you pick this corner, let's say, this is a single point, and then you look at its image, and that will give you a point in X. Okay? If you pick a different point, right? If you pick a different vertex, let's say you picked your vertex over here, that will give you another point in X. So these are going to give you zero-dimensional simplices. Now, if you pick two corners at a time, let's say you pick this one and that one, then you would have two distinct points in X, because we're assuming this is a homeomorphism, so it's 1-to-1. So that will give you two distinct points in X. So basically the way you do it is, when you start writing out the complex K, it will go like this. So a simplicial complex, it's a set consisting of subsets. So the way this would go is, you can always assume you have the empty set, not that it really matters, but you would start with a single vertex like this, and it gets mapped somewhere, and whatever point that is, you call that like P. And then you have set containing P. Then you pick a different vertex. Let's say you pick this one over here, and you look at its image, and it ends up somewhere else. You can call that Q. And then that means in the simplicial complex, you would have set containing Q. Then you do it for the other one. And then after that, you pick two at a time. Let's say you pick this one and you pick that one. Now, when you look at the image of those two, you will end up getting those 2 points again, P and Q, but you're taking two at a time. So you would have set PQ now, and so on. That's the way you do it. If you use all three of them, then you will have 3 points, and then those 3 points taken as a set will be something that sits in script K. And that's only for just one of these mappings. And then you just repeat the procedure for a different mapping. It will, of course, depend on the dimension of this mapping, that if the F lambda is, let's say, mapping a tetrahedron, then you will have more points to consider. You're basically just looking at the endpoints. And that is the way you recreate the simplicial complex from the triangulation. So this is what we've talked about before, but I'm very briefly reminding you of how that works. So that's the corresponding simplicial complex. So anytime you have a triangulation, you get a simplicial complex. And the Euler characteristic is going to be defined as follows. So then I'm going to let n0. This will be the number of vertices. So the vertices are zero simplices in K. And then n1, this would be the number of one simplices. A zero simplex is just a single point, because I want to just quickly remind you the convention is we start counting at 0. So if you have just a single point like P, that's a zero simplex, because that's like you're counting beginning at 0. If you have a one simplex, so this is a combinatorial one simplex in K, then that would be 2 points, 2 distinct points, because 0, 1. So you just count at 1. I'm sorry, you count at 0, and so on. And this will continue until you reach n subscript d, where d is the largest dimension that you see. Okay, and then we define. So we define the Euler characteristic of our space X, but really with respect to this triangulation. It will depend on the triangulation. So with respect to this triangulation, because the triangulation gives you the simplicial complex, and then once you have the simplicial complex, you can count how many zero simplices, one simplices, and so on you have in your triangulation. And then the Euler characteristic with respect to all of that would just be the alternating sum. So minus 1 to the I, it's an alternating sum, n subscript I. And when you add up all of those numbers, that's how you get the Euler characteristic. And the profound observation of all of this, and this is what we can say is the theorem, the nice theorem is that chi is a topological invariant. So i.e. chi of x does not depend on triangulation. So all of these numbers n subscript I depend on triangulation, but the alternating sum that you form out of them does not. And this is the key theorem that we want to prove. And this is going to be our last final lecture on homology, and we're going to use homology to do that before we move to the next topic. In order to prove the invariance of the Euler characteristic, we need some facts from algebra. Some facts from algebra. So the first one that I want to say is that if A is a finitely generated abelian group, then A is isomorphic. So that's what I mean by is isomorphic to a product, or a direct sum is a sum of z's and zn's. So for example, the group is isomorphic to, let's say you have 3 copies of z, then you have 1 copy of z mod 2, and then 1 copy of z mod 5, to use an example. So this is what we call the classification theorem. We actually proved this theorem in topology A through an algorithm. If you're interested, you can find a video on this channel on finitely generated abelian groups, and it will explain how it works. But regardless, this is an extremely well-known fact. I'm sure when you take an algebra course, everybody learns this because it's an amazing theorem. It says that the abelian groups, there's essentially only 2 of them. The group of integers and integers mod n. And if you know just those 2, you know every other abelian group, assuming it's what we call finitely generated. So finitely generated just means that there's a finite set of generators. That just means that finitely generated just means that there is a collection x1, x2, xn in A, so that if you pick anything in A, then you can express A as a sum, let's say a1x1 plus anxn, where the coefficients are integers. So it seems like a basis, but we're not saying it is a basis, because it's not necessarily the case that there's a unique way to do it. There could be more than one way to do it. And the standard example is just to consider, let's say, z mod 3. Okay, the 1 bar, this is just represents 1 mod 3, is a generator. Why is it a generator? Well, because there's only 3 elements. There's the 0, which can be expressed as a sum of 3 of those, or you would write it like this. You would write 3 times 1, right? You're kind of saying that's the element, and that's how many times you're repeating it. 1 would just be 1, and 2 would be 1 plus 1, which would be 2 times 1, like that. So we can see that the class 1 mod 3 is a generator, but it's not a basis like in a vector space, because it's not necessarily unique. So for instance, we can write we can write 1 in a different way. We can also write 1 as doing it 4 times as well. So the representation is not necessarily unique, but that's what it means to be finitely generated, that there's a finite collection of elements so that every other element can be expressed using that. In linear algebra, you call that a spanning set of vectors, but when you're dealing with abelian groups, the situation is more complicated, because in a linear algebra class you learn that if you have a spanning set of vectors, you can just remove the redundant vectors in the list, and then you're left with the basis. But here you cannot necessarily do that. So this is the classification theorem, that A is isomorphic to a product like this. Now, the number of times that you see Z appear in this decomposition is called the rank. You call that the rank of the group. So the rank of A, this is by definition, this is the number of Z vectors that appear. So for example, what we have over here, we would say that the rank would be equal to 3, because we have 3 of those, and these we ignore. These are the finite ones, we ignore those. Another example would be, let's say you want to find the rank of Z mod 3. Well, that would be 0, because there is no Z. It's just a finite group. So then the rank would be 0. It could be shown, it's not immediate, but it could be shown that the rank of a group, of an abelian group, it is well defined. So if A is isomorphic to 3 copies of Z, you cannot make it isomorphic to, like, let's say 4 copies of Z. There's essentially a unique way to do it. It requires an argument, but I think this is a well-known fact from algebra that I'm just going to use it. And then the other thing that I want to say about rank is the following. Well, maybe I should just say a very simple comment that rank versus dimension. So we talk about the rank of A, and this is a finitely generated abelian group. And when we talk about dimension, we talk about the dimension of V, where this is, let's say, a real vector space. Let's say finitely generated also. So it has a finite generating set. But when you talk about a vector space, you talk about the dimension of the vector space, which is how many vectors you have in a basis. So if the dimension of V is equal to n, then that would mean that V as a vector space would be isomorphic to R to the n. So you have n copies of Z. So you might think that rank is similar to dimension. I want to just give you a warning here that we call it rank and not dimension because rank behaves very poorly. So for instance, if V is a vector space and it is a proper subset of another vector space, then the dimension of V will have to be strictly smaller than the dimension of W. The smaller the space, the smaller the dimension. That's what agrees with our intuition. But rank does not behave as nicely. So for example, if you look at the group of integers, the integers which are multiples of 2 is a proper subset of Z. But the rank of the integers is 1, and the rank of the even integers is also 1 for the simple reason because the even integers, that's just isomorphic to the integers again. So you see a very strange situation where you have a proper subgroup, but the rank of that proper subgroup has the exact same rank as the larger group, which is not the way dimension behaves. And there's also other bizarre ways that one has when you're dealing with the rank. So because of that, we call it rank and not dimension. It does not behave the way we want dimension to behave. So that's why mathematicians came up with a different terminology. So this is the other fact. This is the other fact that we need. So let's suppose that A, B, C are finitely generated abelian groups. And suppose that we have a short exact sequence. So if we have a short exact sequence, so then we have this result. We're going to call this the rank sum formula. It's going to say that the rank of the one in the middle is going to be the rank of A plus the rank of C. Okay? So this is the rank sum formula. Now, you probably recall a question on the homework that said that if you assume that C is a free abelian group, if you make that assumption, then you can prove that the one in the middle is isomorphic to the direct sum of A and C, which would then mean that the rank of B, so how many factors of Z does B have? Well, you're going to count how many factors of Z A has, and then you're going to count how many factors C has, and together they will tell you how many factors of Z B has, and that will give you the rank. But the complication here is that this does not have to be a free abelian group. So free abelian would just mean it has a basis, so it would be isomorphic to Z to the n. It could be more complicated than that. So because of that, that kind of argument does not work, but regardless, we still have the rank sum formula. It's also interesting to compare the rank sum formula for vector spaces. Okay, so let me do this. So let us accept this formula for now. Use it to prove topological invariance of the Euler characteristic, and then justify this formula afterwards. So I first want to use it, and then we're going to come back to it and justify where this formula comes from. But it's just interesting to compare this to vector spaces. So let's suppose that instead of having abelian groups, we had vector spaces. U, V, and W are all, let's say, finite dimensional real R vector spaces. And we have a short exact sequence of vector spaces. And then you would say that the dimension of the one in the middle would be the dimension of U plus, I'm writing my U a little bit differently, and the dimension of W. So you could prove it by using the result from the homework that says that because this is free, it is after all a vector space, it has a basis, then the one in the middle is isomorphic to a direct sum of these two. But you can even prove it in a more simpler way. You can just use the rank nullity theorem, which it's kind of funny because here the word rank has nothing to do with the other rank. This is just one of those unfortunate vocabulary situations in mathematics where we repeat the word even though it means different things. So let's say the map from U to V is called F, and the map from V to W is called G. So then the dimension of V is going to be equal to, this is the rank nullity theorem, it would be the rank of G. So again, this has absolutely nothing to do with the rank that we were just talking about for the last 20 minutes. It's just an unfortunate choice of vocabulary, and plus the nullity of G. This is the rank nullity theorem. Now, the rank of G, the image, so the rank of, it's the dimension of the image. This is surjective, so the image is all of W. And so this is just the dimension of W. And the nullity of G, that's the same thing as the kernel. So that would be the image, right? That would be the rank of F, because this is an exact sequence. But because this is injective, the image of U is mapped isomorphically to a subset. So this is just the dimension of U. And as you can see, this proves that the dimension of the one in the middle is the direct sum, I'm sorry, not the direct sum, but the sum of these two dimensions. So proving it for vector spaces is substantially easier than proving it for abelian groups. So what we're going to do is we're just going to accept the rank sum formula for finitely generated abelian groups, and then we'll use it to prove the invariance of the Euler characteristic. So now let us say that X is triangulated. So we're assuming that X is a space that could be triangulated, and script K is its corresponding simplicial complex. Just to quickly remind you, this is a topological space, whereas this is a combinatorial object. It has nothing to do with topology. It's more of a labeling system for vertices and edges and all of that. So now here's what we're going to do with this. Let delta I be the boundary map from the ith chain in K to the I minus 1 chains in K. The notation here, I guess maybe you can argue, is a little bit unfortunate, because if you recall, the way we define the boundary map is it was like an alternating sum of faces, where this was like the 0th face of a simplex, the 1 face of a simplex, and so on. So the notation is a little bit unfortunate because it's not the faces. So these are the faces of a simplex. This is just, I mean, we would typically just call it partial, and then we understand from context which dimension it is. But here it's just useful to label the dimension. So a slight conflict of notation, but we are mathematically mature enough to understand that. I should also say that let's just assume maybe that if I is equal to 0, then there is no C negative 1. So we will just interpret that to be the 0 group. So that would be the interpretation there. And we should also remind ourselves what this is. So this is quite simply, this is the free abelian group generated by all I simplices. Maybe we should say all oriented I simplices in K. And what is an oriented simplex? Well, a simplex, so let's say we have a two-dimensional simplex. So a two-dimensional combinatorial simplex is just a set of 3 elements. An orientation on the simplex is just a word. Okay, so you just write a word using those 3 elements. The convention is that if you flip 2 of these around, then you introduce a negative sign. So that's what we mean by an oriented simplex. So it's not, it would be, you would look at the simplices and you would form these words out of them with the rule that if you were to swap 2 of the elements out of position, you just change the sign on the word. Okay, so that's the way you determine the I-dimensional chains in K. If you're not sure what I'm referring to, I would suggest to go back to the video lecture that we had on simplicial homology. That's the way we defined I-dimensional chains in a simplicial complex. This is the distinction between algebraic topology and combinatorial topology. When we're talking about chains in X, we're talking about the free abelian group that's generated by all mappings from an I-dimensional geometric simplex into X, and that is an enormous group. There's an infinite number of such mappings. But when we have a simplicial complex, when we have this combinatorial object, there's a finite number of simplices, and it's no longer mappings, it is rather the simplices themselves, the oriented simplices themselves that are the objects that make up the group. Okay, so this is the way we define these boundary maps, and this is what we have. So let's write it over here. If you look at Ci of script K, and then you have Ci minus 1 of script K, you have the inclusion map. We need a little bit more space over here. This is the inclusion map, which is, of course, no, that makes no sense. That makes no sense. That's not what I meant. So the kernel of this. So how do we get homology? We get homology by looking at the kernel of this, right? That's how we get the cycles. So what I should say is, here we're going to have the kernel of boundary I, and this is in inclusion. This map is inclusion because this is basically the cycles, right? The ones that get mapped to 0, right? The ones that get mapped to 0. And so the image of this, and then this one gets mapped So I cannot write, you see, the problem would be if I was to write boundary I, if I was to write Ci minus 1k, because this is not necessarily true. This mapping is not necessarily a surjection, but it will be a surjection if I just replace it by the image. So if I just make this the image of this map, then this works out. So this, by definition, is therefore surjective, and its kernel is right there, and that's the inclusion map. So we get a short exact sequence out of that, because the image of this one is exactly the kernel of that one, which is the kernel right there. So we get this short exact sequence. Now, the other way we can get a short exact sequence is by doing this. Let's say I write over here the image of boundary I. No. I'm going to write over here the image. I'm going to write over here the kernel of boundary I. Here, I'm going to write the image of boundary I plus 1. This is going to be the inclusion map. The reason is very simple, because if you take an I plus 1 chain and you apply to it a boundary operator, you end up with a cycle. So the image of this boundary, the I plus 1 boundary map, is therefore a subgroup of that one. So you have that. And here you're going to form the quotient. How do we get homology? We take cycles and we mod out by the image, the ones that arise from an image. So here we would just get homology. So this would be the homology, the ith homology of that complex. And this map that does this for us is the quotient. Maybe to make it even easier for you, we're basically saying this. Suppose A is a subgroup of B, right? This is what we have. This one is a subgroup of that one. And then if we put over here the quotient, then we get an exact sequence. For the very simple reason, because this is clearly surjective, and the kernel of this map, well, what goes to 0? Well, it's all elements of B that get mapped to A, which is exactly A over here. So this is an exact sequence. So by putting the quotient and by using the quotient map, you get an exact sequence. This is exactly what we have here, because you have to recall how we find homology. The way we find the ith homology group is we take this one and we mod out by that one. So that's just homology. So we have these two exact sequences, and these are finitely generated abelian groups, because each of these chains, these are free abelian groups, and there's a finite number of simplices. So if you take the kernel of that, that's just going to be a subgroup of a free abelian group, so it'll be finitely generated. If you take the image of that, that's going to be finitely generated, and if you take the quotient of that, that will be finitely generated. So because these group chains that you're using are finitely generated, in fact, they happen to be free, that it means that the groups in question are all finitely generated. And now we're going to use the rank sum formula. So by the rank sum formula, so by the rank sum formula, we will have the following: that the rank of the one in the middle is equal to the rank of the one on the left, so that will be kernel of this one, plus the rank of the other one, of the image of boundary I. And then we apply the rank sum formula on the second sequence, and we would have that the rank of the kernel of boundary I would be the rank of the one on the left, which is the image of boundary I plus 1, plus the rank of the homology group. By the way, if you're wondering why is it that homology is not necessarily a free abelian group. So for example, we saw that when you talk about the homology of the projective plane, the first homology of the projective plane, you get Z mod 2. So if you're wondering how could this possibly be if all of these groups happen to be free abelian groups, it's very simple, because Z is a free abelian group, and 2Z, that's a subgroup, that's a free abelian subgroup, because it happens to be isomorphic to Z again. But when you take the quotient, it's no longer going to be free. So it's precisely because you're using quotients. The moment you start using quotients, it may not be necessarily free anymore. But this is what we get from the rank sum formula. Let me just double check this again. It's very easy to make a mistake here. So we have the rank of this one plus the rank of that one, and then the rank of the one in the middle. That will be the rank of the one on the left plus the rank of the one on the right. And now we do some substitutions. Well, the first thing I would like to say is this is exactly what we call n subscript I, because n subscript I indicates the number of I-dimensional simplices in K, right? The total number. So the rank is how many such simplices you have. Maybe if that's unclear, this is the free abelian group generated by all such simplices. So the total number of simplices is the number of generators you have. So that is the rank of this group. So this is equal to that one plus this one, and then we can replace this one by that one. So this is what we have. We have that ni. So we have that n subscript I is equal to the rank of this. So we're going to replace it by that. It's the rank. Let me write this one first. Plus, and then copy and paste this one in there. Let me write this one out. That would be the rank of the image of that one. And then plus the rank of the ith homology group. So this is what we get. And now, so what would be the Euler characteristic? So the Euler characteristic, when we use this triangulation, it would be by definition the sum, the alternating sum, going up to D. So we're assuming D is the largest simplex that we see. There has to be a largest one because we're assuming we have a finite triangulation. This would be minus 1 to the I and I. And then we just replace ni, but by the previous equation. So this would be rank image partial I plus rank image partial I plus 1 plus rank of hi of k, like this. And here is what you notice. So these two pieces, they will form what is known as a telescoping sum. It's a sum where every previous term will cancel from the next term. So the I will cancel with the I plus 1. So just to show you what's happening here, if you set I is equal to 0, you will have the 0 boundary, and then you would have boundary 1. When you set I is equal to 1, you would have boundary 1, and the one after that would be boundary 2. Then you would have boundary 2, boundary 3, and so on. But because you have alternating signs, this one will happen with a negative sign, and this is with a positive sign, so you'll have cancellation. This will happen with a negative sign, that will happen with a positive sign, so you have cancellation. So when you do that, everything goes away except the smallest index and the largest index. That's what happens when you have a telescoping sum. Everything goes away except the smallest one and the largest one. So in the end, when you do this, you would be left with, so the smallest one that you see, this is what happens when I is equal to 0, and this is I and not I plus 1 because this one's smaller. So this would be rank of the image of boundary 0, and then it would be, and the largest one is what happens when I is equal to D, and that's what happens with this one. So this would be minus 1 to the D plus 1 to the D, and this would be rank of the image of boundary D plus 1, like this, and then plus, and then we have a remaining sum over here, an alternating sum from 0 to D, minus 1 to the I, rank hi of k. So this is what we end up getting. And, okay, this is what we end up getting. And what you notice next is this is the 0 map, because this is the boundary map from 0 simplices into -1 simplices, but there's no -1 simplices, so this is just the 0 map. And likewise, D is the largest simplex you have. You do not have any D plus 1 simplices, so this is also 0, right? This is just the mapping from the 0 group. So these go away, and you're left with just this. Okay, and what is this? Well, here we're going to say that even though you have a simplicial complex here, you can just replace it by hi of x. So here we're using the fact. So we're going to use the fact, and we never really proven this fact. We never proven this. This was the technical proof that we overlooked. The technical proof that we overlooked was that simplicial homology calculates for you homology. So that if you were to calculate the homology group of X, that would be isomorphic to the homology group of its corresponding simplicial. It would be isomorphic to simplicial homology. We never proved it. It's a very technical, difficult proof. Intuitively, it does make sense because let's say we have a bunch of triangles in some kind of triangulation like this, let's say. And then we're going to draw a cycle. We're going to draw a cycle in X. So let's say these triangles fit together and they form X for you. And now if you have some kind of, let's say, cycle in X, then what you can do with that cycle is you can break it into pieces, right? You just break it into pieces like this. Okay, so you're going to replace the original cycle by a formal sum of chains. And because you're dealing with homology, you can choose a representative. So the red cycle can be represented as a sum of these, but then every blue one can then be homotoped out further to run along the edges. So you can just take the blue one and sort of homotope it out so it runs across the edges like this. Homotope this one out so it goes along the edges. This one sort of goes along the edges like this. And then what you end up seeing is that you can take this, the original cycle, and you can just homotope it out without changing the homology so that it runs along the edges. So that means that instead of considering all possible paths in your space, you can just assume that the paths are running along the edges in the triangulation. That's sort of the idea behind why this works. It seems pretty convincing, but that's not a proof, and a lot of effort is required to make that rigorous. This is you can find it in Alan Hatcher's book, and it just takes pages upon pages to go through that. And what we did is we sort of just accepted this fact. So if you're willing to accept the fact that the homology of a simplicial complex is isomorphic to the homology of a topological space that it triangulates, then you've shown that the Euler characteristic is a topological invariant. Because what we've just calculated is that chi, the Euler characteristic, is equal to, so these are zeros, and it's just an alternating sum of the rank of the homology groups. Okay, so let's say this. So we see from here that the Euler characteristic is equal to the alternating sum of the ranks of the homology groups of X. Therefore, it is a topological invariant. So that proves why you always get the same number no matter how you triangulate, because in the end, it comes back down to homology. So that's a nice derivation. That's a nice way to conclude our discussion on the theory of homology. But what remains is to justify the rank sum formula. That's what remains, and that's going to be the interesting part. So that's what we'll discuss next. Of course, the remaining question is how to justify rank sum formula. And you can give a more elementary proof of this, but I specifically wanted to show you a categorical proof, which nicely fits with the theme of the semester. It's a very nice proof. It will go over some of the ideas that we've talked about before. So that's why I want to do it specifically this way. Even though you can give other proofs that one can say are a little bit more elementary. But you really want the kind of proof that you get the most out of, and I think this is the one you get the most out of. So here's how we would approach this. I'm going to let AB this is going to be the category of abelian groups. And then we're going to define another category. Let's call it vec subscript r. And this is going to be the category of real vector spaces. And the idea for what we're doing is vector spaces, they're similar to abelian groups, but they are simpler. They're a lot simpler. And we're going to define a functor that will take us from this category to that category. So we're going to convert a problem among groups into a problem among vector spaces. And then once we convert it into vector spaces, it's going to become easier to solve. So this is what we call a categorical approach, where we're going to define a functor from this category to that category. And here's how we're going to do it. So the name of this functor, we're doing it with real vector spaces, but you can also do it with vector spaces over different scalars, but let's not go there. So the name of this functor is called hom r. I like to say homming on the right. Homming on the right. That's the way that I like to say it. Other people, nobody uses that terminology. So how does this work? So this is going to be a functor from the category of abelian groups to the category of real vector spaces over the reals. And so to be a functor, I have to tell you how you take a group and how you turn it into a vector space. So here's what the functor does. So given a group, so given an object in the category of abelian groups, the hom functor is going to assign this. That's why I write it hom.r, because the idea is that the functor, you're feeding this object into hom, and now you have this. So this is going to be the, you can say this is just the homomorphisms. This is the set of f from A to R, where this is a homomorphism. And then what we realize is, observe that hom AR has the structure of a vector space, of a real vector space. So how does this work? Well, to give a structure of a vector space, you have to define vector addition. So the elements of these are going to be vectors. So let's say you pick two vectors in hom. Let's call them f and g. So this means that f is a homomorphism from A to R, and g is a homomorphism from A to R. So how do you define f plus g? Well, you define f plus g the obvious way, that these are two functions, and then you're just adding the two functions together. So f plus g, the way this would act on an element x of your group, you would just simply apply the first function and you would add the second function. And this, of course, makes sense because these happen to be real numbers, and then you're adding two real numbers together. So you have vector addition, and then you have scalar multiplication. So the other thing that you need is, let's say you have a vector, right? So this is a vector. It's an element of hom. And then you have a scalar. So c is a scalar. So how do you define c times f? So c times f will have to be defined as another element in hom. So that in particular, it has to be a mapping from A to R. And it's defined in the obvious way. The way it acts on x is you apply the function, the original function to x, and then whatever that is, you multiply by c. And this makes sense, of course, because this is a real number multiplied by c. And it is a very easy exercise. Like, it's so easy that one does not even do it. But it's a very simple exercise to verify that this becomes a vector space, that hom AR becomes a vector space over the reals. So you have defined this mapping that takes an object in this category and it gives you an object in that category. But in order to get a functor, you also have to explain. So let me just remove all of this. So the other part is we have to explain what this hom does to morphisms. So to define to describe Hom as a functor, we also need to explain how it acts on morphisms. So let's say we have A and B, and we have a morphism between A and B in this category. So this is just a homomorphism between two groups. So how do we get a homomorphism, or what we would say a linear map, between vector spaces? So when we apply Hom to A, we're going to get Hom AR. And when we apply the Hom functor to B, we get Hom BR. And now we're going to get something that is a little bit unusual because we've never had this before. Normally, up to this point, all of our functors, they preserved the direction of the arrow. This is going to be a functor that reverses the direction of the arrow. So it's going to be a functor that goes like this. And a lot of the times, the induced morphism, we often call it F with a subscript, with a star. That's what we do when it goes in the same direction as the arrow. When it gets reversed, it's common to put the star as a superscript. So this is going to be the induced linear map between these two vector spaces. So this is going to be what is known as a contravariant functor, as opposed to a covariant functor. So as opposed to covariant functor. All of the previous functors that we've looked at, the abelianization functor, the fundamental group functor, the homology functor, and so forth, all of those functors that we previously looked at, those were covariant functors. They preserved the direction of the arrow. This one reverses the direction of the arrow. But other than that, it's the exact same idea. It now will go the other way. So we have to define how to do it. And because this is algebra, it's always the obvious thing. So we're going to pick an element. We're going to pick an element over here. So let's call this one. So let's call this beta. And if it's an element in this one, what does that mean? That means that beta is going to be a homomorphism from B to R. That's going to be beta. But we also have a homomorphism from A to B. Maybe we can even write it like this. We call that one F. And how do we get a homomorphism from A to R? Well, it's the obvious one. You compose. You first go F, then you go beta. So this is going to be, you first go F, and then you go beta. So this is going to be, so this one is going to be beta composed F. So this is exactly what we're calling F superscript star of beta. That we do it by composition. But the composition goes the other way. If you go back to the fundamental group functor, the way F star was defined, it was defined by composition, but it was really the other way around. Because this is a contravariant functor, the composition goes this way. The beta, you can see it's not F composed beta, they get interchanged, it's beta composed F. So, and you can check, right? So so what do we have to check? So it's an easy exercise, and I think maybe we can put this on the homework. It is an easy exercise. Now, it's easy, but you have to do it. You have to verify the properties, and that's what you do in order to learn this kind of stuff. But it is an easy exercise. There's nothing clever. You just have to carefully go through and check every one of the properties. It is an easy exercise to show that Hom R is a functor, i.e., it preserves commutative diagrams, and that it preserves the identity morphism. Another thing you have to check, you also need to check that F star is indeed a linear map. I forgot to say that because this is supposed to be a homomorphism between vector spaces. So this is supposed to be a linear map. So you have to verify that F star will satisfy the properties of a linear map. So there you have it. You have constructed a functor that takes you from the category of abelian groups, and it takes you into the category of vector spaces. Now, there is an additional property that this functor has. So let's give this functor a name. Maybe I should say an observation about this. You can also consider Hamming on the left. But this would actually be a covariant functor, and I do not want to go there. We're not doing it like that. So let's not go there. The two functors are actually very different from each other. It's very interesting that it feels like it's almost the same thing, but they're they behave very differently from each other. Okay, so this is what I wanted to say. So this functor Hamm functor is often denoted by, so you would have your object and you put a little star on top and you call it the dual functor. You're going to call that the dual functor. So you would write, instead of writing Hamm AR, you would rather write A dual. Okay, and if you have a group homomorphism, then you get a homomorphism of vector spaces going the other way from the dual of B to the dual of A, and you call that the dual map, right? You would just refer to this as the dual map. This is the homomorphism, and this is the dual of the homomorphism, which is now a linear map between their duals. Okay, so we have this. So now that we've came up with the notation, let me say an important property. So this dual functor satisfies an additional special property. Namely, it preserves short exact sequences. Now, what do we mean? What we mean is, if we have a sequence of groups, abelian groups, that is exact, and it's common not to even write the names of these maps unless you have to. So then you will have a sequence going the other way. This is going to be a sequence of vector spaces, is also exact. So if you have a sequence, an exact sequence of abelian groups, then the dual functor will convert that exact sequence into an exact sequence of vector spaces. By the way, it is not difficult to show that the dual of the zero group is the zero vector space. So basically 0 goes to 0, but these are different zeros. This is the zero group, that's the zero vector space. Yeah, so this is what you get. And the interesting part here is this claim is very easy to check, except exactness at A dual. So what I mean is, if you want to show, so we're accepting that this sequence is exact. So you want to show that this sequence is exact. So you have to show that it's exact at C star, that it's exact here, at this one. In other words, the map from C star into B star is injective. Okay, that's easy to do. You want to show that it's exact at B star, which would mean the image of the incoming map is equal to the kernel of the outgoing map. And then you have to show that it's exact here, which would mean that the map going from B star to A star is surjective. And what we're saying here is this one is easy to check. In other words, it's just a matter of following definitions. This one is easy to check. And this one is surprisingly hard to check, contradicting a very important rule in algebra that everything is trivial. So this is going to be one of those circumstances where that is not trivial to check. You actually have to come up with an elaborate argument in order to prove that. So what I'm thinking is, maybe I'll show you that C star, that it's exact here. I'll do half of a proof why it's exact at B star, and then to show that it's exact at A star, that would probably make more sense to put that as a homework problem with some hints and some steps so you can figure that out yourself. So we can call this, maybe we can even call this like a theorem, that the Hom functor preserves short exact sequences. Actually, this is interesting but not required. Let me just say this. In fact, one can show that if a functor preserves short exact sequences, then it must preserve all exact sequences. And that seems like a grand, amazing claim, but it's actually not too difficult to prove. If you're interested, you can look on Wikipedia something called an exact functor. So an exact functor, it's a functor that preserves exact sequences. And there's a very elegant proof that if you have a sequence in general, like it's a very nice type of an argument. So if you have some kind of sequence in general that possibly goes on and on and on, and it's an exact sequence, then you sort of replace these by the kernels and the co-kernels, and you kind of go something like this, and then you kind of go back like that, and then so you basically sort of triangulate your exact sequence with a lot of zeros, and then you use the fact that it preserves, you sort of reduce it back to short exact sequence. It's a very nice kind of an argument that you'll be able to find on Wikipedia. You can also find it in Hatcher. So if you look around in Hatcher's book on algebraic topology, I do not know exactly where it is in the book, but basically just randomly go across the pages until you see some kind of diagram, which is a bunch of arrows going like this, and then you have sort of arrows going like triangles, and then you have a lot of zeros, and that's basically what he's arguing. So it's just a nice fact to know that if short exact sequences are preserved, then all exact sequences are preserved. So what I basically mean is that if you have, let's say, an exact sequence of 4 abelian groups, then and it's exact, then this one is going to be exact. So that's why we call it an exact functor. But normally, it's harder to prove that something is exact directly. It's easier to show it as exact for short exact sequences first, because then you have more assumptions about the maps. And then from there, it will just follow more generally. So let me just show you the 2 easy ones. So I think what I need to do here is I need to introduce some names. So let's call this map F. Let's call this map G. So then this map would be G star, and this linear map would be F star. And we want to show that G star going from C star to B star is injective. We're claiming it's exact at C star. So you say that you have 2 elements, let's call them gamma 1 and gamma 2 in C star, and G star of gamma 1 is equal to G star of gamma 2, right? That's what we want to do if we want to show that something is injective. We take 2 elements in here, we map it to the same thing, and we argue why gamma 1 and gamma 2 have to be the same. So this implies, now you just use the definition of the dual functor. So the definition of the dual functor, this would be gamma 1, you interchange them. So it's gamma 1 composed with G is equal to gamma 2 composed with G. And now what you basically argue is, since gamma from B to C is surjective, why do we know that? Well, because G, this is an exact sequence, so G is surjective. So since this is surjective, we can cancel the G's. So gamma 1 is equal to gamma 2. So when you have a composition of functions, you can cancel on the right if it's surjective, and you can cancel on the left if it's injective. Now, if you're bothered by that argument and you've never seen it before, then it's actually quite simple. So since gamma 1 composed G is equal to gamma 2 composed G, this implies that gamma 1 and gamma 2, so what are gamma 1 and gamma 2? So these are elements of C star. Okay, so gamma 1 and gamma 2 they happen to be mappings, homomorphisms from C to R. That's the definition of the dual of a group. So they happen to be mappings from the group into the reals. So that means they have to be the same on the image of G, because it's gamma evaluated on G. So they're going to be equal on the image of G, which is a subset of C. I'm sorry. Yeah, that is correct, right? So the image of G, that would be a subgroup of C. So they're equal on that subgroup. But because we're assuming that this is surjective, this is actually equal to C. So they're equal, they're the same thing on the entire, they're not just equal on the subgroup, they're equal on all of C. So it's the exact same function. So this is the easy part. Now the other one, I'm only going to do half of the argument. You can do the other half, but we have to show, if I want to show that it is exact at B star, so we will have to show, so to show that the image of G star is equal to the kernel of F star, right? That's what we have to do. Now, since the original sequence is exact, we know from the original sequence, so if we go back to the original sequence, if we do F followed by G, we get 0. So G composed F dual is 0 dual. But this is a functor, and it's a contravariant functor, so it reverses the arrows. So we get F star composed G star is equal to 0 star. And it takes a little bit of an argument that this 0 is referring to the 0 homomorphism between groups, and this 0 star, that's just going to be the 0 linear map between vector spaces. So basically 0 goes to 0. Not difficult to show. And then, so what does this show? The image of G star, it gets mapped to the kernel, because F star applied to whatever G is will give you 0. So the image of G star is therefore contained in the kernel of F star. And look at that, we've done half of the argument. So then you have to do the other half. The other half will, of course, take more work, but it's doable. And this is the part which is hard to show. So this is the one that's difficult. So let's maybe talk about the difficult part. And you'll actually see perhaps what makes it difficult. So the hard part, and this is what I was saying, that it makes sense to put this on the homework. So the hard part is to show that F star from B star to A star is surjective. So we're going to pick, so given, let's say, an alpha in A star, we need to find a beta in B star with F star applied to beta is equal to alpha star. Now, what does that actually mean in a diagram? So what this really means in the diagram is, this is our original sequence. We're assuming that A gets mapped injectively into B. We're calling that F. So this is just a part of our sequence. We're not really concerned about the other piece. We're just looking at this beginning piece of it. So we have this. And then we're saying that given alpha, so that would mean that this is a map into the reals, alpha. So we're saying that we can find a beta. We can find the beta from this one to that one. That makes the diagram commute, because this condition is just beta composed F is equal to alpha. I wrote alpha star here, but that makes no sense. So you can see alpha is equal to F composed with beta. So this is sort of a, you can say, a lifting. So basically, any alpha can be lifted through F. It's kind of like a lifting problem. So this is the reason why it's somewhat tricky, because you're arguing that it is possible to construct such a beta that does it for you. So let us accept the fact that the dual functor preserves short exact sequences to conclude with our proof. And it's going to be a very nice proof, very categorical, very modern, and it's the kind of proof you can actually learn a lot from. So first, some simple observations. The first one is, if you start with the integers, the group of integers, and you take the dual, then that would be isomorphic to R as a vector space. Why? It's actually very simple, because the dual, these are homomorphisms from Z into R. And in order to describe a homomorphism, you only have to describe what it does to the generator 1. Once you know what it does with 1, you know what it does everywhere else. So if you know that 1 gets mapped to, let's say, pi, the number pi, not the map pi. Well, maybe I should not call it pi, it'll be confused. Let's say it gets mapped to square root of 2. Then that means 2 will have to be mapped to 1 plus 1, the image. So 2 is equal to 1 plus 1, and 1 plus 1 will therefore get mapped to this, 2 square root of 2. And that will mean that negative 2 will get mapped. It's a homomorphism. We'll have to go to the negative of that, and so on. So if you know where you're mapping the generator, then everything is completely determined. So the homomorphism is completely determined by the image of the generator. And the image of the generator could be any real number. Okay, so homomorphisms from the group of integers into the reals is completely determined by what happens with the generator. Because you can assign any real number, those homomorphisms are determined by a real number. So the dual of the integers is therefore, as a vector space, isomorphic to the reals. The other one that we want to look at is Z mod n. As a vector space, this will be isomorphic to the trivial vector space. You can use the exact same argument. Let's say we do Z mod 3, and we map it into the reals. So everything is determined by the generator, so the class 1 mod 3. Let's say 1 mod 3 is being mapped to the square root of 2. So what does that mean? Well, we know that 1 has to get mapped to square root of 2, but then that would mean that 2 will have to be mapped to 1 plus 1, so that would be 2 square root of 2, and then 3 will have to be mapped to 3 square root of 2. But the problem is 3 is also equal to 0 mod 3, and so it has to also be mapped to 0 square root of 2. And then you notice what the problem is. These are not equal. So you have a contradiction that arises. So in other words, there is no homomorphism that will send mod 3, which will send the generator 1 to square root of 2. The only number it can go to, so let's call this number r. The only number, if it goes to r, then this would be r, this would be 2r, this would be 3r, which has to be the same thing as 0r. But the only way this can happen is if r is 0 itself. That's the only homomorphism that will avoid giving you this kind of contradiction. So the only real you can send it to is just 0. So there's only one such homomorphism, and it's the trivial homomorphism. And so as a vector space, that's just a trivial vector space consisting of the 0 vector only. Okay, that's very simple argument. If you do not like the argument, I mean, it's fairly simple, but here's a somewhat clever argument that uses the dual functor. So here's the way that it would go. You would start with this sequence. So you would map Z into Z. This is multiplication by n. That's the multiplication by n map. This is an injective map. And the image would be nz. So now you take the quotient like this, and you have an exact sequence. And if you dualize, you would have this. Now look at this. We said that this is R, right? This is R. And we said that this is R. Now because this is a linear map, and it's surjective, and these both have dimension 1, this has to be a isomorphism. And if this is an isomorphism, this forces this one to just be 0. It has to be the 0 group, because this is an isomorphism, so this is 0, and that one has to be 0. It has to be 0 on the left and right. So that is a fancy way of proving this using the exactness property of the dual functor. Another property that we need here is that if you have two abelian groups and you form their direct sum and you dualize, you will get a vector space that will be isomorphic to the direct sum of two vector spaces. So there's two ways to prove it. You can prove it a very elementary kind of a way where you sort of consider homomorphisms from the direct sum into the reals, and you show and you actually construct an explicit isomorphism with the direct sum of those two. You can do that. There's nothing wrong with that. But I think a more elegant way to do that is by going back to the exact sequence. You can say that you get an exact sequence like this, where this is just a map that sends A to A comma 0, and this is just a projection map that sends A comma B down to B. That's just a projection onto the second coordinate. This will form an exact sequence for a very simple reason, because the kernel of this, if we want this to go to 0, it means the second coordinate has to be 0, and the first coordinate could be anything, which is exactly the image of the incoming map. If we dualize, then we would get an exact sequence that goes like this. Right? We just dualize everything. But because these are vector spaces, it automatically means that the one in the middle has to be isomorphic to the two on the outside. And there we go. We have just proven this nice fact. So what's the consequence of all of this? So here's the consequence. So putting all of these together, so let me remove this. So this is the consequence. If A is a finitely generated abelian group, then those simple observations imply that the rank of A as a finitely generated abelian group has to be equal to the dimension of its dual. Okay, and this is very easy to see. It's just easiest to look at an example. Let's say A is isomorphic. Let's say we have 3 copies of Z. We have 1 copy of Z mod 2, and we have 1 copy of Z mod 3. Then the rank would be then the rank of A would be equal to 3. If you take the dual, well, the dual of a direct sum is the direct sum of the duals. So this would just be the duals of each of these. We're just using property number 3. I know we proved it for 2, but once you prove it for 2, it's true for any finite number, because if you have 3 things like A, B, C, it's just a common trick, right? A, B, C. You just pair these together as D, and then you prove it for 2, and then very common trick in math. You only have to prove it for 2 things, and then you kind of keep on pairing it like that. So now these are isomorphic to R, right? So these are just R. And the finite ones, the ones that are mod n, they become 0. So you see what you get in the end. You get a vector space that's isomorphic to a 3-dimensional real vector space. So then the dimension of the dual would be equal to 3. Now this is nice because we've said that rank does not behave nicely, whereas dimension does behave nicely. And we're converting a rank type of statement into a dimension statement, which behaves a lot more nicely. So here's how we prove the rank sum formula. So here is a really modern categorical approach to proving the rank sum formula. So suppose A, B, C are finitely generated abelian groups, and we have a short exact sequence of those groups. So then, by applying the dual functor, we get a short exact sequence of real vector spaces. And in fact, we can say finite dimensional real vector spaces. So thus, the dimension of the one in the middle is equal to the dimension of the 2 on the outside. Because doing this for vector spaces, that's the easy one, right? The dimension of the one in the middle is the sum of the 2. That's what we've discussed before. But now we get to say our previous observation that the dimension of the dual is equal to the rank of the group. And then you can just replace this by the rank of B, and that's equal to the rank of A plus the rank of C. And there we go. We have proven the rank sum formula in a fairly elegant manner. So, and the good news is, this is, maybe we can conclude with this. This is the good news. We have concluded with homology theory. No more homology theory. We have said a good amount of stuff on homology, and now we're going to move on to something else. We can, of course, continue to discuss homology. There's many more things that one can talk about. One can talk about something called relative homology that we mentioned many times. One can talk about something called cellular homology, which is the best way of actually computing homology. Then there's something called the Eilenberg-Steenrod properties, homological properties, and so on. Basically, what these are is, it says that any theory of homology that satisfies certain properties will have to be isomorphic to each other, things like that. So there's actually many things that one can talk about, but I think that for the first course, for the first time that you're learning this, we have covered the bare minimum, the bare essentials of homology theory, so that you hopefully have some intuition and some experience when it comes to using it and doing some kind of computations. So we're going to finish with this, and with the next lecture, we're going to move on and talk about manifolds, and especially smooth manifolds.